When we play something and interact with the vast world of video games, it's normal to think at some point, how do zeros and ones become video games? After all, computers are essentially thinking stones that obey what we tell them to do. How did we get out of manipulating zeros and ones and get to the games we have today, with millions of polygons on the screen at the same time? How do we manage to make graphics so realistic? My name is Rafael, and welcome to the Code Byte. To understand the whole process, we need to see the computer up close and understand a little more about its history. The binary system is, well, a system based on just two digits, zeros and ones. When the zeros and ones are combined, they can represent different information. For example, in John von Neumann's machine, the instruction set describes the number 00000101 as the operation code, or opcode for short, responsible for performing the addition of other values that are in the computer's memory. This example is just a binary number used to describe an information or an action. Each computer architecture has its own set of instructions and actions that it can perform. Some other examples in architectures will be left in the description in case anyone is curious about it too. We currently use a family of architectures called the AMD64 that are used by Intel and AMD processors. You may also have heard equivalent names such as x64 or x86-64. Different architectures have different functions and commands to interact with the computer. We won't delve too deeply into different architectures here, but knowing they exist is essential to understand how computers work and what it can do. While we can try to program a computer using only these basic instructions, which we call machine code, this type of code is not very readable for the average person. After all, it's just numbers, zeros and ones. To improve this a bit, we build equivalent of these codes and name the commands. After that, the code gets a little more readable and we start to have something interesting. It's like creating layers on top of layers. This slightly more readable layer is called an assembly code. Assembly is a powerful tool, and it can do everything a modern language does. However, the cost of this is labor and time. Implementing a complex system using assembly not only takes a lot of time and effort, but it also generates code that's difficult to maintain and with many repetitions. It's important to make a note here before we continue. Some amazing programmers have managed to do wonderful things using only assembly, like for example, the developer Chris Sawyer, who made the Roller Coaster Tycoon game by himself using assembly for performance issues. Everything in computer science depends on the situation, the need, and the goal of your project, so keep that in mind. However, with these problems mentioned, scientists and programmers began to think about another layer of abstraction for computers. Until now we had the hardware, the physical part of a computer. After that, we saw that machine language emerged with a bunch of zeros and ones, and now we had assembly. A new layer would serve to make the code even easier to read and to join instructions that were always used together. This layer would be much closer to our real language, such as English, which humans can read, write, and understand with ease. So this new layer was called high-level language. There are several high-level languages, and each one has a specific function and was created for a specific purpose. At that time, languages such as Ada, Algol, Basic, Prolog, C, Fortran, and Pascal began to appear. All of these languages are extremely important for what we currently have today. However, let's focus on just one here, the C programming language. C is a general-purpose language that was developed in 1972 by Dennis Ritchie, who had already worked on several other projects and languages. It's much more readable than languages in the previous layer and abstracts several concepts, things like loops, conditions, functions, and even memory management. Even if you don't know how to program, just by looking at the code you can understand the basics. The C language is essential for us to understand how games work. Nowadays, many games are still written in C or in variations and inspirations of C, like C++ and C#. But that's not the reason for us to focus on this language. To understand why, we need to accept two things for now. The first thing is that drawing something that represents a 3D object on the screen is not an easy task, and the second thing is that we have graphic cards that help us with this task. While the processor CPU does complex and diverse operations very well, it can calculate with good performance what is needed to reproduce 3D graphics. Graphics card, also called GPUs on the other hand, specialize in metrics and vector calculations, as well as other techniques that are sorely needed to display a 3D image on the screen. These cards can do everything a processor can, but they can do those specific functions with much more performance. However, leaving aside all the complexity of the hardware and how these cards work, how do we even program a GPU? Just as programming languages have evolved to the point where the programmer doesn't have to worry about zeros and ones, so have graphic cards. With the development and evolution of these components, different specifications began to emerge on how a programmer should be able to send instructions to it. You may have heard of OpenGL, Vulkan, or DirectX. These names are specifications that describe commands that programmers can use to communicate with and program the GPU. And the best part about this is that these specs are implemented in C. All these specs manage to do similar thing but in different ways. Want to draw a polygon on the screen? Maybe multiple polygons to build a 3D model? This is possible, but it takes time, dedication, and a lot of effort to understand how the whole process works and how you can use it to your advantage. Some cards implement only one of those specs. However, most modern cards support OpenGL, Vulkan, and DirectX. This is a very dense, extensive topic with a lot of math and linear algebra involved. I'll put a few things about this in the description. While, for example, OpenGL and Vulkan allow us to implement modern games with our cards, we've run into assembly-like problem. We spend a lot of time and effort to do this from scratch every time. We don't want to have to implement the same system to handle animations in dozens of games if the animation system is going to be the same. We don't want to implement physics calculations multiple times if we can do it once and reuse the code. The same goes for audio, collisions, and other spheres of game design. We like the ease and we like to have tools at our disposal without worrying about the details. This facility can be achieved through the game engines. Game engines are programs built with the intention of facilitating game development. The gaming market has grown immensely in recent years, and with it, the need for specialization has also grown. A while ago, games were made by only one or two people, and although we have cases of indie games that are developed by a few individuals today, most games are produced by big studios. While Super Meat Boy, Freeze, Hades, and The Outer Wilds have their place in that list and their achievements are gigantic, a game like The Last of Us Part 2 couldn't be produced by just one person. For this, it's necessary to have people who understand sound, animations, art, without worrying necessarily with how the zeros and ones work, and a good and well-developed engine can be the difference between a success and a failure of a game. But what if you don't want to do this all from scratch? Is there any options available for this? Some engines like Frostbite used to develop Battlefield or ID Tech used to develop Call of Duty are proprietary, and some studios don't even reveal the name of their engines, as is the case with the Naughty Dog Studios, responsible for the Uncharted and The Last of Us series. However, there are great and free options on the market that are used in big games and projects. The Unity game engine is the most popular option. It was used in the production of Hearthstone, Ori and the Blind Forest, Cities Skyline, Cuphead and Hollow Knight, and other great titles. There is also the Unreal Engine, which is a great choice for 3D games. It also carries big titles such as Octopath Traveler, Batman Arkham City, Kingdom Hearts 3, Final Fantasy VII Remake, Borderlands and Fortnite. Some options are geared toward 2D games, such as Godot, Game Maker's Studio, or even RPG Maker. These options are responsible for City Game Studio, Webbed and Corpse Party respectively. Other engines have already been very famous among certain companies and communities, such as the Source Engine, developed by Valve for games like Half-Life, Portal, Garry's Mod, Team Fortress and Counter-Strike, and CryEngine that was developed by Crytek and used in games like Crysis, Far Cry, and Rise Son of Rome. The list of options is extensive, and it all depends on the tools that you have at your disposal and the details and needs of your project. However, if you're starting now to do game development, it is recommended that you stick with some basic options like Unity. These options have been around long enough for you to find research online, tutorials and solutions for common problems. It's much easier these days to start developing games and put into practice a project you like. All this thanks to the effort made for a long time by programmers and computer scientists. Do you have any other information that you think is relevant about the topic? Or do you want to add your favorite games to the list? You can share these interesting things here in the comments section. I am Rafael and that was The Code Bites. See you next time.